Assalamu alaikum everyone. This is Abdul Fatah from BS Mathematics 7th semester, and together with me is Abdul Rab from MS Mathematics 2nd semester. So we are here to present our presentation on the topic of fast transforms in image processing and compression, their restoration and the image resampling. So this is our topic, and we will be presenting our semester presentation given by Dr. Sajid Khan at Sakaraibiya University. So let's start.
So this is our first slide. I am defining what are the details of article. The article title is Fast Transforms in Image Processing, Compression, Restoration and Resampling. So in these slides we will learn how in this article the author is talking about compression and what methods we are using to restore an image and why we need to resample an image. And the author's name is Leonard Yerersky, Tel Aviv University, Israel, and he has published this article in Advances in Electrical Engineering. This is a very good journal in Hindawi journal, and he published this in 2014. But it has a very good content, and let's see what the article has. Fatah?
Yes. So here we are going to introduce our article that we are going to present. So before we start, we would like to tell you that why actually we are using transforms and which kind of transforms we are using. As you seen in first slide, our topic is related with the first Fourier transforms. So why actually transforms and which kind of transforms we are going to use in digital image processing. So the reason that we are using transforms is that the invention of digital image processing is actually depending upon the transforms, because it started due to these fast Fourier transform in 1965. This was the first phase in 1965. The Cooley and Tuckey, who were working on the fast Fourier transform, actually worked on Fourier transforms, and they actually invented this field, digital image processing. And in this wave from 1965 to 1970, they actually invented lots of transforms which helped them in engineering and many other fields. So in second wave in 1970, which was inspired by the engineering communication and telecommunication technologies and some other applications of image processing. So there were also a huge number of transformations that were invented. Those were comprised of Walsh-Hadamard transform, Hart transform and slant transform. And the main reason of invention of these transformations were the data compressions. Due to data compressions, these transforms were created, and this period actually ended with the introduction of DCT. The DCT is a discrete cosine transform, and this was one of the best transformation of that time in 1970s period. So it was also the reason that the JPEG and MPEG format of the image and video and audio processing were created also. So that period actually ends in 1980s, and then the third wave of digital image processing actually was initialized. So coming to the next slide.
So in this we see the third large wave that was obtained or dominated by wavelet transforms in 1980s. After this period, we see the first is Fatah said there were few transformations is heart transformation and which was the other there are
Head-
three
head merge.
head merge.
Head
But
merge,
then
Walsh.
in 1980s we see a wavelet transform. It was a very good transform which was very much used and it produced good local representation of signals and images in contrast to global. Now here local representation means that it was very good in small chunks of data, not comparatively in the big data results. Now if we move to main distinctive features of transform is their energy computation compatibility, and by energy compaction we refer to the compatibility of transform to redistribute the signal energy into small number of transform coefficients. This is the energy compaction through which we will use and also see how wavelet transform perform and how much important these wavelet transform are. And let's see in next slides we will also see still we are on introduction that why transform and which transforms, and as we move forward we will be watching what comes next. Let's see. Now this is the table.
So as we
for the-
discussed,
Yes.
so as we discussed about some types of the transformations that which transformations and these three periods were invented and their applications. So we are going to actually highlight their applications, main features, and what is their work related to image processing. So the first comes the discrete Fourier transform, which relevance to the image optics represents the Fourier transform. So the main characteristic of this discrete Fourier transform are these, that cyclic shift variance, but this is very weak at the boundary effects because it has less effect on boundaries. So the and main applications, so the Fourier transform and discrete cosine transform is also a, you can say it's a kind of it's Fourier transform, but it is somehow different. It's a particular
in discrete
case you
Fourier
can
transform
yeah.
we can see that there are
That-
both terms na? Like in summation a n sin x n plus b n cos x. So there are both representation of sine and cos as well in
Yeah,
the
we can
overall
say
sum. But
that-
in
that-
discrete cosine transform we will have only one term, that is cosine.
Cosine, just
We will
cosine.
neglect sine term.
Yeah.
So this is called discrete cosine transform
discrete
mathematically.
cosine
And
trans-
let's come what it is relevance to image topics. It represents the optical Fourier transform.
and
and it is-
main features and characteristics are cyclic shifts with double cycle, virtually not sensitive to boundary, but it is unlike to the discrete Fourier transform, which is actually weak at the boundary, but this is not like that one. So the main applications of these both transforms, discrete and cosine transforms, are analysis of periodicity, fast convolution and correlation, and third one is the fast and accurate image resampling. The resampling that we will actually study or have a look on this resampling topic in further slides. And then image compression, we will also discuss that. Image denoising and deblurring, we will also discuss them later. These are actually the applications of these discrete Fourier and discrete cosine transforms. It means we can actually handle these kind of issues with using these kind of transforms. So the second comes discrete Fresnel transform, and this is represent optical Fresnel transform, and its features are computable through discrete Fourier transform and DCT, discrete cosine transform. We can actually, it means we can compute discrete Fresnel transform with the help of discrete Fourier transform and cosine transform.
Which we have defined previously.
Yeah, in first two we have discussed them. So the application of it is a numerical reconstruction of holograms. So the third one is Walsh-Hadamard transformation. So relevance to the image optics, it has no actually relevance with image optics. So its characteristics are that binary basic functions provides piecewise constant separable image band limited approximations and its applications are image compression and coded aperture imaging.
Right.
And the last one is not last, but we still have some hard transform and discrete wavelet transform. Is subband decomposition. It's the relevance to the image optics, and its characteristics are feature, you can say, are binary basis functions and fastest algorithm, multi-resolution, shift invariance in each particular scale. And its application is actually that we can use this transform, hard transform and other wavelet transform in signal and image wideband noise and denoising. It means we can use it to add noise or remove the noise from the image, and even we can use it in image compression, that we actually discuss what is image compression in further slides. So it's also used in image compression as well.
So this was the table 1 first part. Is still the table 1 continues. So let's move in its next part. Here is the next part. So in table 2 we will see table 1 completely. What part of topics here?
Yeah, it's ended here.
Okay.
So
the next is table 2, and it represents the selected fast transforms most relevant for digital image processing and their computational complexity in one-dimensional denotations. Now in the name in column we will have the following transforms, that is discrete cosine transform, and as we discussed earlier that there are not both terms. In discrete Fourier transform we will have both terms, that is cosine and sine, but in cosine transform we will have only cosine term.
only cosine.
And this is how we use summation, and there is also amplitude in the transform. And here we see that what is the computational complexity. So it is written that discrete cosine
sample.
So it is a global applied to entire signal of n samples, real numbers of operations, and CGDCT of log n. And here we have in real number operations local column we have C DCT means discrete cosine transform, which must be less than W of is Z. But in discrete Fourier transform we see there is
exponential
of this
some complex number which also contains if we look at in a trigonometric form, it will contain both a sine and cosine term, as you said earlier.
The most famous identity, Euler identity, that is e power
iota theta is equal to sine theta plus
iota cos theta. No, cos theta plus iota sine. Iota sine theta.
Vice versa.
Yeah. Now but it's global. We will have complex numbers. In cosine transform we had real number operators, but in discrete Fourier transform, as we see that iota is still running here, is visible. So it has complex number operations. Its complexity will be computed through complex numbers or their magnitudes. And general shifted scales, discrete Fourier transforms are also there with these parameters that are u delta x and v delta p of sampling. Further, it is also cited in different articles, but we had this information in this article, although it is very deep topic. In further articles it is also discussed that are being cited in this article. Now we move next and see here more characteristics.
So there is also a discrete, as we see the discrete Fresnel transform was one of the transform that we have selected.
And this is the continuation of, I think, table 1.
Yeah. No, this is not a table 1. This is continuation of the table 2. So in this we are actually looking at the definitions of the transform that we discussed in table 1. So in this we are actually looking at the definition of discrete Fresnel transform. So that its definition for a conic discrete for Fresnel transform DFRT is alpha R, and just summation and the alpha AK. You are looking at this expression. Yeah, Okay, this one.
There is also touch is very
Yeah.
like to.
This is the definition of the canonic and
Mm.
discrete fractional, and for the
Convolutional.
convolutional discrete fractional transformation we have this one definition.
Hmm.
So this is also a complex number operation like the discrete Fourier transform, not like the discrete cosine. Now we have a Walsh-Hadamard transform. So Walsh-Hadamard transform we have this one definition,
Hmm.
and for Walsh transform we have this one, this alpha r, yeah, this one,
And for Almond we will have this.
this
Now
one.
their Km and especially R are again defined here.
Yes.
As we can see, this is in another loop. We loop within loop. So this is how
A
it
nested
is
loop,
computed.
you
How
can
the
say.
transform will be
Yeah.
applied. So I guess it is very complex comparatively to
So
previous ones.
the last one is the Hart transformation, the simplest discrete wavelet transform. It is
This is
also-
what we were talking about with
Yeah.
wavelet transforms.
It means Hart transform is a type of a wavelet transform. So this is the definition of Hart transform, where HARK means this one. This definition of H of R index in K is equal to this one. So addition operations only. Here are only addition operations. So coming to the next slide.
This
So
is
now
the
now we will discuss about the compression of the images.
Yes.
As we in previous slides we discussed about the compression, and we look also at some of the transformations which has applications in image compression. So now we'll actually look at the definition of what is compression, and how this is done in image processing. So Abdul Rab,
yes.
please describe this one.
So in compression, we see that first we have an image. We
Yeah.
convert that image in a matrix or an array, as we have seen
3D array.
throughout this course. Then the set of image pixels. We apply fast orthogonal transform. That is, any transform is we saw discrete cosine transform or discrete Fourier transform. Then we get what effect on the image. There is that the shrinkage of data.
Yeah.
The data shrinks, and in the
This
second
is the
step
main.
there,
This is the main process of compression, because
yes, we
the
see
data
that.
is actually shrinked in this process, right?
Yes, and we also do the scalar quantization of transform coefficient. As quantization, we have already discussed that we would do what we discretize the amplitudes of the data in each pixel. Then we do apply some certain threshold that after this we will neglect these values or we will get these values, and so we move forward from this step to the next step, that is entropy or encoding the quantized transform coefficients, and hence we get the compressed bit stream. Now here we see that the image is ready to be sent, and
Yeah.
the picture has been compressed. So now we have very less storage of the image it will be taking, so we can now send it anywhere as per our application or consignment. Now what will do the next person when he will or she will receive the image?
Yeah.
So they will have to perform another inverse operators. Now let's see set of reconstructed image pixels. How? Now we will move from here, as I have circled here. Now the next person that receive will start from here. He will receive a compressed bit stream.
Yes.
Now he will apply a entropy decoding, because we had entropy encoded. Now he will apply entropy decoding. Now dequantization of the transform coefficients
right.
and inverse fast orthogonal transform. Here we had applied.
It means
fast
whatever
orthogonal
the transformation we have applied, we will apply now its inverse, so
Inverse.
that we can get actual image on which we transform. We applied the transformation.
Yes. Now in the here we will get the matrix that we had sent here.
Yeah.
This is the star point, the matrix star. Now here we will receive the matrix, star. That is our how the flow diagram of image transform coding and reconstruction. The first was the coding of the image, and in the last step from here, as we see from here to here, we moved of what reconstruction of the image, right? And this is how compression works, is we see, but we do click on buttons, but at the back end this process happens. Now this is the compression results.
So as you can see, there are 4 pictures, A, B and C, D. So these are actually the results of the compression. So in the first picture you are seeing it is our test image which we are going to compress actually. So in second picture there are many methods and many transformations for compressing the image, but in this we have used the global discrete cosine spectrum in second picture. So the first picture have turned into B by using the global discrete cosine transform spectrum. So if we want local compression, or we also say a blockwise transformation, like in C you can see image C, we have divided the picture into blocks. So now in picture D it is compressed blockwise, or you can say it is compressed locally. So in global we compress the whole pictures, but in global and local we actually compress the blocks in which the picture is divided actually.
So in overall results of these, we see that the better results will be given by blockwise image or local representation, because in global we see that at the corners, we see at borders, there will be more not good results. It is not means it is insensitive to the borders. But as we see the blockwise or local representation, there is a sensitivity at the borders as well. We will get clear picture. Each pixel is broken down, the entire matrix or array is broken down into blockwise, and each block is coded. So in there will be less impact of neighborhoods, so hence each pixel will be of good results. The lesser the order of matrix, the better the compression results. But here we see that the most usually that is we saw in the article, 8 by 8 cross matrix is used for compression. And let's move next now. Here is the transform domain of filters for image restoration and enhancement. So we will use 3 filters of these.
So
yes,
here are some of the filters that we are going to introduce. So the first one is the empirical veneer filter. The definition of empirical veneer filter is this one. So
in this we are getting output results of each pixel. Now there is a maximum function we can see, that we will never get a negative, because maximum of 0 comma this number, that is SPN square minus SP noise or SPN square. So if we consider that somehow that there is the result, say suppose -1, so maximum function will do what? It will always maximize the result.
Yes.
Means the minimum threshold will be 0.
Yeah. So second one is the signal spectrum preservation filter. So you can see here it will also, it is just same like the empirical veneer filter, but just here is a square root of maximum of this term. So third one is a rejecting filter. So the rejecting filter is actually a piecewise type of function, so in which we are
just dividing by ISFR.
Yeah, just dividing by ISFR. Which
if our is input is square root, absolute square root is greater than SP noise, so we will reduce this, otherwise we will do nothing, just replace all in everywhere 0 in our output image. But in some applications we say, as we see here, it is written here, I have highlighted from a script from the article, that in some applications image denoising using the spectrum preservation filter is called soft thresholding, and rejecting filter is called hard thresholding. Here 53, 54 are citations where further we can see what the soft thresholding and hard thresholding is and about these filters. Now version of these filters are filters that combine image denoising, debildering and image enhancement by means of p-law nonlinear modification of corrected signal spectral components. Now here we see that it is the combination of both. What? Last two ones, the signal spectrum preservation filter and rejecting filter, and we will get this. In this we can see in here that if this happens in this S input square is greater than SP noise, we will have this S input divided by SFR, but we see that we get this here, otherwise we will have same 0. Next.
So coming to the next slide.
Now
so here is the picture A and picture 2. What actually there is a difference between them is the first one has a noise and the second one has no noise. So what in picture B, we have removed the noise from the picture B by using some filters. So this is actually a banded noise removed. So in first you can see there are also strips as like a
shiny
noise.
strips.
Yeah.
Yes.
This picture is of a Mars, and which when brought from there, this contains
basically when we brought from the Mars, as the NASA received the data, we had this before picture. So we applied these filters. One of these filters, as we discussed now, there are 3 filters were there.
So by applying these filters, we have got a perfect result. And after getting a clear picture, we have a picture B, which is, you can see the better result as compared to the part A.
Let's move to any next example if available. Yes, wire noise removed. So here we see that this is the original scan. So whenever we scan a photo, an old photo, or in maybe in paper sheet or anything like this, so we do what, we get little noise over there. Like you see, there is continuous noise everywhere, almost surely everywhere is noise. You can see here and here we see are not clear or visible. So after applying one of the filters as we discussed here, 3 filters, so we get a very good results. See, the skin is very clear, the hair are very clear, and when compared to original, look at the original skin, there is continuous little noise there. So this noise is called Moray noise, and this is how we have removed, or maybe the person that of that article has put good efforts to remove this type of noise as well.
So now coming to the next slide, now we are actually going to define the image resampling and build continuous image models. So what actually the image resampling is, it is the process of deriving pixels values for a new image from an existing image is called image resampling. For example, if we have a test image which is original one, if we want to create a new image from that one, that will be known as a resampling. There are 2 types of resampling the image. The one is upsampling and the other is a downsampling. The upsampling is that when we increase the pixel size from the original one, then we say that's resampling, known as upsampling. If we are decreasing the size of the image from the original image, then we say that is downsampling. For example, if we have 1,000 by 1,000 pixels image, original image, if we are making a new image from that pixel or that image of 2000 by 2000 pixels, then that will be known as upsampling. If from the same image of 1,000 by 1,000 pixels we are going to create a new image which is of 500 by 500 pixels, that will be known as downsampling.
Yes, thank you. Let's move to the conclusion. What we have learned today, there were two fundamental features of fast transforms were energy compression capability and fast algorithms for transform computation. And in next we learned that FFT fast Fourier transform are best
Okay.
for compression, restoration, reconstruction, and resampling.
Resampling.
Two fundamental but the most important FFTs or fast Fourier transforms are discrete Fourier transform and discrete cosine transform. And we had a lot of data. If I could show you people the article, there were many pictures as well, but we restricted ourselves to make this slide of almost 30 minutes. There were many topics, but we have highlighted a few of them and discussed this picture as well.
Yeah.
And this schematic diagram, how compression and depression is occurring, and this is how the compression results we discussed also. And this was the filters. We also did empirical Wiener signal, and we also saw this image discuss and also see now. So we did not had the time enough to include this picture. We also had
this is also a same one that we actually include.
Yes,
related to
pictures
that
giving good results. This is a very big article, so it was a good cover up of this article. And thank you very much for listening. And it was very nice and good presentation.
It was a good experience actually for us
to have this presentation. Thank you. Thank you.
Thank you so much.